All right, good morning, folks. I always like to play a game when it snows. Do you think local school systems, whatever they're called, district schools, like K to 12, open or closed today, do you think? They are open, which was a surprise to me. Last year I played this game, and I think we were maybe going to get 3 centimeters of snow, maybe that day, and they canceled the school for the day, which kind of pissed me off. But today is a lot better. My son goes to school. I want to be safe and stuff, but at the same time, certainly the buses can get through a snow day that looks something like today. The university is also open, which sometimes can be a surprise. They've been a lot more trigger happy with closing schools for storms lately, but here we are. In any case, we've got just a couple lectures left to the term, which is great. And what we've been talking about most recently is a new topic, and we've been talking about combined loading. Last day, I introduced combined loading on tension members, where we looked at some kind of interaction equation, where we're basically looking at the cumulative utilization, you could think of it that way, of the tension relative to its tension resistance, and the two moments about strong and weak axis relative to their strong and weak axis moment resistances. And we looked at linear strength interaction, which was for class 3 and 4 sections. And we looked at nonlinear force interaction, which is for class 1 and 2 sections. When we can develop that full plastic stress distribution above and below the neutral axis, we start to get some terms in the moments 0.85 and 0.6 on MF and MY, MFX and MFY to account for the nonlinear interaction, but then we also have to check bending only strength. Today we're going to start talking about combined compression and bending. And really what we're going to focus on today, because almost everything's the same, is we're going to look at the introduction of these two new terms, U1X and U1Y. And because we're looking at strength as well as stability, instead of just checking strength and stability, we had a yielding of the tension flange and buckling of the compression flange. Here we're going to have similar. We're going to have yielding of the compression flange, buckling of the compression flange in a lateral torsional mode, but we're also going to have the potential for flexural buckling exacerbated by the presence of a strong axis or weak axis bending moment on the cross section. So there are 3 limit states that we're going to look at today, and these U1X and U1Y factors that start to come into the interaction equation, and those are the things we're going to focus on today. So whenever we have combined compression and bending, these things tend to be called beam columns. Beams take bending, columns take compression, and so if we have something that takes bending and compression, we call them a beam column. Okay, they're pretty common in the example here that I showed the other day, a crane supporting column with a standoff. There are going to be some point loads acting on the standoff out here, and that eccentricity is going to cause some bending, and that presence of that vertical force is also going to cause some compression. So there's going to be a bending moment diagram for that member and a compression in that member as well. More common in buildings, again, I showed this example the other day. We've got some columns that are perhaps carrying the vertical load from the roof, and we've also have this glazing support system. These horizontal members are called girts. They're going to take the pressure from the cladding, distribute those loads along those members, and then those members are going to transfer that force into those columns. And so in addition to that vertical compression force that the column has to carry, it's also going to be carrying some transverse or lateral loads, we might say, which would result in some bending in that section. Another similar case here, we've got another cladding support system. We've got these point loads coming in wherever we've got these little brackets. Again, these columns are supporting loads from the roof as well as transverse loads causing bending. And we're going to look at an example of how we might consider the strength of a member carrying those kinds of loads today. All right, so basically after this morning, you should be able to describe the mechanics behind the linear strength interaction equations for combined compression and bending. Describe and account for the influence of compression on the maximum bending moment in members with compression and bending. That's something that we're going to bring up today. This point has everything to do with the U1X and U1Y values that we're going to be talking about today. Basically, whenever we have a bending moment and deflection from bending, the compression is going to make the bending worse, and we have some factors to account for that. And most importantly, you should be able to apply the linear strength interaction equation to check a member that has combined compression and bending. Today we're going to focus on the effects of compression on the bending moment and the linear strength interaction equations. The stuff we're going to talk applies, this part here, when we're going to introduce U1x and U1y, that applies to all beam columns. But the last objective here, this applies primarily to class 3 beam columns, where we want to keep the maximum compressive stress less than yield, because local buckling is going to get in the way. Okay, next day we'll talk about nonlinear interaction for class 1 and 2 beam columns. Does anyone have any questions about why these 3 things are important before we get into the material for the morning? Okay. So again, we'll revisit for the last time, I hope, some basics of stress analysis. Last day we looked at a very similar problem. We had a beam that was carrying a uniform moment and a tension force. Oh, there we go. And today we're just flipping that tension force into a compression force. Okay, so we've got bending and we've got compression. Where is the maximum normal stress going to be on this cross section? If we were to sketch the cross section, where's the maximum normal stress going to be? Well, if we look on a plane through here, we've got a compressive stress, which is going to cause a stress distribution something like this. And if we've got a bending moment, we're going to have a stress distribution something like this, right? So we've got compressive stress from bending, we've got tensile stress from bending, and we've got axial compressive stress from the applied compression force. And as long as the section remains linear elastic, and these stresses, when combined, don't exceed the yield strength, we can apply elastic superposition to get a stress diagram that looks something like this, right? Where we've got predominantly compression in the top half. Here we've got compressive stress. Here we've got tensile stress. And this is just basically the opposite of what we talked about the other day. The other day, when we had tension and compression, there was less compression and more tension. The tension force helped to reduce the compressive stress, which helped lateral torsional buckling, helped stabilize the beam. But we were worried about the yield strength, perhaps, of the bottom flange and tension. Today, the compression force is adding to the compressive stress that comes from the bending moment. And so we're making the stability of the beam worse, right? So here we've got top flange in compression. When the top flange is in compression from bending, we have potential for lateral torsional buckling. And the presence of this compressive stress is just going to add to that stress that wants to cause lateral torsional buckling. If we have a beam that's fully laterally braced against lateral torsional buckling, then we start to just worry about cross-sectional strength as we did the other day. Okay, so going through the same motions as combined tension and bending, we've got an axial force of compression, which is CF over A. We've got a bending stress from, we've got a compressive stress and a tensile stress from bending, which was MF over SX. And if we look at the combined effects down here, the compression flange has a stress of MFX over SX plus CF over A. Very similar exercise to what we did yesterday. Sorry, not yesterday, Monday. We've got some limit states to look at, just like we did before. If we have a fully laterally braced beam and we're not worried about lateral torsional buckling, in that case, all we need to do is keep the compressive stress less than or equal to the yield stress for the beam. And going through the same motions as the other day, we divide through by the phi Fy term to get MFX over phi Sx Fy. That's the fully laterally braced moment resistance. You might say class 13.5 MR for class 3 sections, right? And then we have phi A Fy, which is the tensile resistance. But when we write CR, usually we have phi A Fy divided by some junk in the denominator. And if we have a really, really short beam, let's just assume that it's short and buckling is not an issue, then all the junk basically turns into it just turns into 1 because here I guess we've got the junk in the denominator is 1 plus lambda to the 2n all to the 1 over n. If lambda is really small, it means the column's really short, and so lambda becomes 0, and this becomes 1. And so we could say for really, really short columns, we have essentially the compressive resistance in the denominator as long as buckling is also not an issue. Okay, so the way that this gets written when we talk about the strength of beam columns in S16 is we've got the factored strong axis bending moment over the moment resistance for a fully braced class 3 beam plus CF divided by CR if lambda was 0. Okay? And basically the reason we write it this way is because we're trying to check cross-sectional strength. Cross-sectional strength doesn't have anything to do with stability. We're just trying to limit the stress to be less than or equal to Fy. And so if we're going to check it, we're checking this from mechanics of materials, but if we write it in terms of the interaction, we write it in this way. Okay? It just makes it easier for us to think about in terms of factored force divided by factored resistance. Does anyone have any questions about that concept before we continue on? Okay. So basically, we're trying to prevent yielding, and we do that by checking this interaction expression. We also have the potential, as the other day, to develop lateral torsional buckling. And so for beams that are unbraced against lateral torsional buckling, all of a sudden, again, this expression becomes the phi times the critical compressive stress in the flange that would cause lateral torsional buckling. The other day, we said, okay, let's assume that FCR, or let's rewrite phi FCR as MRX over SX for an unbraced beam. Today, we're going to do something a little bit different, though it's going to be more or less the same. We're going to divide through by here, both the left-hand side of the equation, the right-hand side of the equation. We're going to divide by the phi FCR term. And the other thing we're going to do, this is an approximation and a conservative one. FCR is the moment resistance for an unbraced beam divided by SX. That's the critical stress that would cause lateral torsional buckling of the compression flange. We're going to assume that that's more or less equal to the torsional, or what would I say? We're going to assume that that stress is going to be equal to either the torsional or weak axis compressive resistance divided by the area. Okay, so whatever stress on the cross-section would cause weak axis or torsional buckling, whichever is critical for the boundary conditions, we're going to assume conservatively that that stress is equal to the same compressive stress that would cause lateral torsional buckling. They're similar, right? If the beam wants to buckle about its weak axis, the flanges are kicking out sideways. And if the beam wants to experience lateral torsional buckling, the compression flange is kicking out sideways. They're similar enough failure modes that we're going to assume that that stress is more or less the same for both of those. So in doing so, we get phi SX FCR on the denominator of the moment resistance term and phi A CR on the compressive resistance term. And if we've defined it that way, then basically we get the moment resistance, right, calculated in accordance with clause 13.6 for unbraced beams for class 3 sections. And over here we get the weak axis or torsional buckling mode, okay, or buckling resistance. 95% of the time it's going to be weak axis buckling. We talked about modes of global buckling, and for wide flange sections anyway, the weak axis buckling was usually the one that was governing, even if torsional buckling was something that we would be considering. Okay, so now for lateral torsional buckling, we've got lots of compressive stress. The presence of the compression on the column makes it worse. We want to make sure that the combined stress is less than the stress that would cause either weak axis buckling of the compression flange or lateral torsional buckling of the compression flange. If we make those stresses more or less similar, we can express it as an interaction between the strong axis bending moment and the unbraced resistance of that beam and the factored compression force divided by the weak axis buckling resistance of the column. Are there any questions about that concept before we continue? So these are all very similar. The other day, tension made strength worse. Today, compression makes strength worse. On Monday, tension made lateral torsional buckling better. Today, compression makes lateral torsional buckling worse. The same limit states, just checked slightly differently. One other thing that's different between beam columns and members that carry combined tension and bending if we didn't have any axial force at all, I'm just going to say, let's just pay only attention to the moment on this beam. Let's assume it's a constant moment. Why not? If we have a beam with a constant moment, it's going to bend, right? And so if the beam is going to bend, then it's going to have a certain displacement. We'll call that maximum displacement here, delta. That's the mid-span deflection caused by just having a uniform moment acting on that beam. So from MFX, we get a uniform bending moment diagram. But because the beam is in a displaced configuration, when we add a compression force and we consider equilibrium at the middle of the beam, the moment at the middle of the beam is not just the applied moment anymore. If we consider this local displacement of the beam, we've got the moment present, plus we have a moment arm now of CF acting over delta, and that's going to add to the bending moment at the midsection. Up here, the additional bending from CF is not as much, and at the supports, the additional bending is 0 because the local deflection there is 0. What we have is an additional bending moment diagram then to consider from the presence of the axial force acting over the local displaced shape. And the shape of that bending moment diagram is more or less the same as the displaced configuration of the beam. Okay? So that poses a bit of a problem because normally we just say, okay, there's MFX. Let's make sure the beam column is strong enough to take MFX. However, MFX is actually whatever's applied from the first order analysis, we'll say, from the analysis of the beam with the uniform moment, plus the CF times delta term. Normally, we would sometimes call in mechanics CF, we'd sometimes call that P, and we usually use small delta to represent local deformations along the beam length. And so this additional moment, or sometimes we call it the amplification of the moment, due to the presence of an axial force on the displaced shape of the beam, we call that P delta effect, or P small delta effect. Sometime in your career, you're going to hear P delta effect. That's what this is representing in terms of local displacement of beams. Does anyone have any questions about this concept? It's kind of, I'm waving my hands a little bit, but from a mechanics perspective, I hope it's clear. We've got a displacement that causes additional bending under the presence of the axial force. Are there any questions about that before we continue? We have to consider this additional bending somehow. And we could do a very advanced analysis, or we could try and simplify things a little bit to make our lives a little bit easier. What we're going to do is we're going to say MFX plus CF delta. We're going to rewrite that as some amplification factor, U1x times MFX. Okay, so we're trying to replace the additional moment with an amplification factor that's going to be bigger than 1. And in that case, the additional moment here is just whatever U1 minus 1 is times MFX. And so we've just replaced CF delta with U1 minus 1 times MFX. Now, I'm going to get hand wavy here in a moment because in order to figure out what U1x should be in the context, we have to look at graduate level material and differential equations and that stuff that I don't even think I've seen in a classroom, the derivation, though I've read it before. Basically, we have to consider the presence of the moment, CF delta and MFX, as well as whatever moment is present due to the curvature of the beam. If we solve that differential equation, we get that the moment at mid-span, maximum moment, the curvature times the second derivative of the displaced shape, is whatever the applied moment is, the uniform moment in the section, divided by the cosine of the square root of CF over EIX times L over 2. Okay, so we're basically just, I'm skipping all the math there to show you what the maximum moment is. The maximum moment at mid-span is EIX times the second derivative of the displaced shape. That's equal to what we're trying to calculate, which is U1x MFX. So basically, all this stuff that gets multiplied by MFX is equal to that U1 factor. Okay, so we could write U1x as 1 divided by the cosine of CF, square root of CF over EIX times L over 2. Now we're going to do some simplification. We'll remember that, or we'll define the Euler elastic critical buckling load about the strong axis, which is what we're looking at here. We say, okay, the elastic buckling load that would cause buckling about the strong axis is pi squared times EIX over L squared. If we look at this and we substitute and rearrange some things, what we end up with is that U1x is equal to 1 divided by the cosine of pi over 2 times the square root of CF over CEX. Okay, so that's as simple as we're going to make it theoretically speaking, and again, I'm not presenting really the theory behind it. What I'm trying to suggest here is that if you go through the math based on the free body diagram and the differential equation, we can figure out what amplification factor we can calculate to multiply MFX by to get the total moment acting on the section. Super clear, right? All that stuff. Now, back in the day, when S16's been around since the 40s or 50s, they didn't really have calculators then. They had slide rules. When you have slide rules, it's hard to do cosine, and it's hard to do square roots. What's easier to do is simple division. And so what they did was they simplified the expression to be something a little bit simpler. I'm just going to rewrite this for a bit as, I guess I should probably have an extra slide in here. They simplified the denominator here. Why do I have a keyboard up now? That's not what I want. There we go. This is approximately equal to, you could demonstrate through small angles, 1 minus, oops, I'm on the wrong, there we go. This is approximately equal to 1 divided by 1 minus CF over CEX. Okay, that's a gross simplification, I would say. It works well for really small axial forces, and it works poorly for really big axial forces. But it's something that they could do by slide rule easy enough back in the day when they're doing their design calculations. So this is what CSA S16 gives us as an expression for U1x. And that means, now that you have the context for where U1x comes from, you can forget about this other more complicated expression. Okay, so when you're doing beam column checks, do not use, even though it's more accurate, the expression shown on the left. We're going to be using 1 over 1 minus CF over CEX, which is a simplification used in S16. Okay, so what we went through, basically, we said we've got a P delta effect we have to consider. It makes the moment bigger. We're going to consider that by multiplying the uniform moment by a factor U1x, and based on some math and gross simplification, we can calculate U1x as 1 over 1 minus CF over CEX. Okay, so now we have a tool that we can use to approximate the so-called P delta effect to get the amplified moment on the cross-section. Anyone have any questions about any of those concepts before we continue? Okay. That works for a uniform moment. Sometimes we have uniform moment and sometimes we don't. Sometimes we have a moment gradient or a linear bending moment diagram. And I guess I should get rid of the scribbled out 1 here. The way that we try to account for non-uniform bending moment diagrams is by modifying the U1x term by an omega-1 term. Very, very similar to the omega-2 that accounted for moment gradient for lateral torsional buckling, except now we're looking at a moment gradient factor that accounts for the P delta effects and the stability of our beam columns. If we have a non-uniform moment, we have a slightly different. We might think that the maximum moment would be down here, and it would be for a uniform bending moment. But if we have a linear bending moment, the maximum moment is actually somewhere up here, which is further away from where the maximum displacement is, right? The maximum displacement is here. The maximum moment is somewhere up here. And so how much additional moment is present depends on the shape of the moment diagram. For a uniform moment, it's times the maximum displacement. For a double curvature moment, there's not going to be any additional bending at the middle. It's mostly going to be at the ends. And so we've got a factor that we're going to multiply U1x by to account for the fact that linear bending moment diagram is going to reduce the effects of CF times delta. And we're going to calculate omega-1 as 0.6 minus 0.4 kappa, again where kappa is the ratio of the two end moments, M1 over M2. Okay? And I believe that's, again, a negative value for single curvature, because if the moments are equal, we should get omega-1 as 1. So, because the moment diagram is different sometimes, that reduces the severity of the P delta effect, and we modify U1 with this omega 1 value. It's a bit more complicated for other situations, but CSA S16 gives us some equation or just some values to use. If we have a uniform load, or more simply a distributed series of point loads, we're just going to take omega 1 as 1, so we're not going to modify U1x. For a single point load anywhere along the length of the beam, pardon me, that's a little bit better in terms of p delta effects, and so they say we multiply the U1x value by 0.85 to reduce the effect of the p delta moment acting on the column. Okay, so we've got U1, which accounts for the CF delta. In a simple term, we modify it by omega 1 depending on the shape of the moment diagram. Omega 1 is 1 for a constant moment, which is shown here. We calculate it as 0.6 minus 0.4 kappa for a linear moment. And then for the shapes of moment diagrams, it looks something like this. We have values specified in the standard to use. Are there any questions about those concepts before we continue? Okay. So that basically, I don't know why this is here. Oh, that's why it's there. We already talked about cross-sectional strength for braced beams. We need to make sure that they're not yielding the compression flange. For unbraced beams, we need to make sure that we're not going to develop some lateral torsional buckling mode. But the other thing that the presence of this moment does, even if we don't get lateral torsional buckling or weak axis buckling, we could exacerbate, make worse, the buckling mode about the strong axis. Okay, so normally we'd calculate CF perhaps based on the FEX value that we might calculate. We calculate FEX for strong axis flexural buckling. We calculate CF for strong axis flexural buckling. The presence of that moment is going to make the column want to buckle about the strong axis at a smaller force. Again, because the presence of that moment is causing an earlier initial yielding. And so in addition, we also have to check a limit state that we don't check for tension, because tension does not cause flexural buckling, and it's called overall member strength, which I hate as a term, but that's what they call it. I would call this just strong axis flexural buckling is really what it's intended to capture, strong axis flexural buckling, because the presence of the moment makes the buckling resistance lower than it would be if the moment was not there. So that gets us into what CSA S16 tells us. S16 clause 13.8 is all about axial compression and bending. We're just going to focus on the stuff from 13.8.4. It's for linear strength interaction, and that applies to class 3 sections because we never want to exceed the yield strength on class 3 sections, because if we do, we end up experiencing some local buckling. So I'm just summarizing everything we've already talked about, and I'm throwing in the U1y MFy over MRy term. It's the same pretty much as what we would have had for tension and bending, except now we've got U1y. So the interaction diagram is almost identical to what we had for tension members, tension and bending for class 3 sections, except now we've got these U1 terms. In fact, this is the same as what we do for tension members. It's just worded as we calculate the compressive resistance for lambda is equal to 0. For strong axis moment resistance, we take the fully braced class 3 moment resistance, SXFY, weak axis moment resistance, SYFY times phi, and then we've got the U1x values that we're going to be calculating, but they're not allowed to be less than 1. It might seem weird to have a U1 value less than or equal to 1 because we're talking about amplifying the bending moment on the cross section. But if we account for omega 1 for a single point load, or if we calculate it for a linear bending moment diagram, it is possible to get values of omega 1 less than 1. It's possible to get omega 1 values less than 1, and therefore also U1 values of less than 1. But in this case, if we do calculate something to be less than or equal to 1, we're not allowed to take that value. We have to take a value that's at least 1 when we're checking cross-sectional strength. Again, we're using fully laterally braced and moment and compressive resistance for lambda is equal to 0 because it's a stress check. It's not a stability check. We're checking the maximum stress on the cross-section, making sure it's less than or equal to the factored yield strength. Okay, so check 1, CF over CR, U1x MFX over MRX plus UNY MFY over MRY. Use these values for CR, MRX, and MRY. This is the easiest possible check to do because these are the easiest calculations, except we have to calculate U1x and U1y as well. Does anyone have any questions about what we need to do here to check cross-sectional strength before we continue? Okay, this is a boring lecture because I show you the same thing 3 times in a row and just tell you what's a little bit different. For overall member strength, that's that strong axis flexural buckling that we're trying to prevent when we have a moment in addition to the compressive force. We're going to calculate the strong axis compressive resistance. We're going to focus. This is really for strong axis buckling, and so we use CRX for no weak axis bending. If weak axis bending is important and overall member strength is important, then lateral torsional buckling is going to govern anyway. This is really just for strong axis flexural buckling. We calculate CR based on the strong axis flexural buckling load. So we calculate FEX and then calculate lambda using FEX to get CRX. You can go back to lecture 22 to look at how that works. MRX is still the braced moment resistance because we're really just adding the additional moment to see how much worse the flexural buckling mode is going to be. Except that if we do have a value of U1 that gets calculated to be less than 1, the idea there is that the shape of the moment diagram reduces the overall compression, which helps to reduce the effects of moment acting on the column as far as flexural buckling goes. So we're allowed to take, for example, here a value of 0.8 if we were to calculate it because it helps the stability of the member, whereas we're not allowed to do that for cross-sectional strength. Okay, so the calculation of U1x and U1y seems to flip-flop a little bit, but we're looking at flexural buckling, and really we're trying to make sure that CRX is okay whenever there's the presence of a strong axis bending moment as well. Any questions about what we're trying to do with the interaction equation here before we continue? So the last one, lateral torsional buckling. If you have anything that's unbraced 95% of the time, lateral torsional buckling is going to govern. We'll see this work out a little bit more in terms of the strength checks in the lecture on Friday. But this is what we're looking at here. We're looking at stability of the compression flange. And so if the column is in compression and it's going to fail about torsional or weak axis flexural buckling, we're looking at the minimum compressive resistance from clause 13.3, which is usually weak axis or torsional buckling. We're looking at the unbraced moment resistance about the strong axis. And I mean, for the most part, you can ignore the weak axis moment, but it's going to make things a little bit worse. But we just calculate that based on SYFY. This is where things get a little bit annoying because first we had to calculate UNX and U1Y, and they had to be at least 1. Then we would calculate them, and if they're less than 1, that's fine. Now all of a sudden, if U1Y is less than 1, that's fine, but if U1X is less than 1, that's not okay. Okay, so we flip-flop on these U1X values quite a bit from limit state to limit state. But the reason that we're not supposed to use U1X is less than or equal to 1 is because when we calculate the unbraced moment resistance, we're already calculating an omega 2 value there that has to deal with how the moment diagram results in, helps with the stability of the beam against lateral torsional buckling. And the logic here is they don't want to double count the moment gradient in stabilizing the beam. And so they say this has to be, U1x has to be less than, or at least equal to 1.0. So we're not being too unconservative by double counting the moment gradient and the stability of the beam against lateral torsional buckling, as well as the stability of the column about flexural buckling. Okay, so if I was to summarize, for the most part, cross-sectional strength, CR is going to be big, MRX is going to be big, and so it doesn't govern that often. As soon as we start to look at overall member strength, the compressive resistance goes down because now we're considering buckling and not just yielding. So it's more likely that that's going to govern compared to cross-sectional strength. And then if we look at lateral torsional buckling, CR is probably going to go down more. MR is going to go down to the unbraced moment resistance. And so 95% of the time, I would say lateral torsional buckling is going to be the limit state that's going to be the worst when calculating the strength of beam columns. Okay, but we still have to check them all because the limit states will vary from time to time. Are there any questions about what 3 limit states we need to check or how to check them before we continue on. Okay. The last thing I'm going to say is that we're not doing anything weird here in terms of linearizing a nonlinear interaction equation. You'll recall the other day that when we had a beam column, or a member under combined tension and bending, the shape of the interaction might look like that, so we had to have a linear diagram, but we weren't allowed to exceed the bending only strength. We also have to make sure we're not exceeding the bending only strength, not because we have any nonlinear effects, but because it's possible here, if you were reading this standard and you said, okay, I'm going to check my member as a beam column, if CF is 0, and I don't actually have any compression acting on the beam column, I just have strong axis bending only, or maybe weak axis bending only, or maybe I've got strong and weak axis bending. If CF is 0 here, and you happen to calculate U1x and U1y values to be less than 1, then you're exceeding the biaxial bending or the bending only strength because of the U1 values that you're trying to calculate. Okay, so you can accidentally overestimate the strength of your beam column using the overall member strength interaction if CF is 0, and that's why we have to check to make sure that MFX and MFY are less than or equal to MRX and MRY when we combine them together. Okay. So when we calculate U1, S16 tells us exactly how to do that. In clause 13.8.5, it says U1 is omega 1 divided by 1 minus CF over CE, where we calculate CE as the elastic buckling resistance. Important here is that we do this for the axis of consideration. If we want U1x, we're going to calculate omega 1x based on the moment gradient, or the moment diagram for strong axis bending, about strong axis. And we're going to calculate CE about the strong axis. So CEX would be pi squared E IX over LX squared. And if we're going to do the same thing for Y, then we'd use the moment diagram for weak axis bending, CEY, and then IY and LY for the buckling about the weak axis. Okay, so U1x and U1y are calculated the same way. We might just have slightly different moment diagrams and slightly different properties to consider about the two axes. Omega 1 is 1 if we have a uniform moment. Otherwise, if we've got a linear bending moment diagram, we calculate it using the equation I showed you before, but we're not allowed to take something less than 0.4. And then if we've just got a series of point loads or a UDL, 1 for a single point load, 0.85. Okay, so relatively simple to figure out what omega 1 should be and how we use that to calculate the U1x and U1y values we might need. Okay, so S16 tells you everything that I've already told you, but has that brought up any additional questions before we get to the example? Okay, so all we're going to do today is we're going to focus on calculating the U1x term, and it's relatively new. All the other stuff we've already kind of looked at for tension, we'll unpack a little bit more in the next lecture. We're going to look at this situation where we might have, we'll say, an 8-meter tall column, or at least there's 8 meters between the center of the supports for the column. It's a W310 by 64 made from ASTM A992 grade 50 steel, and it's going to carry specified forces. We've got a snow load, 300, a dead load of 600. Those are compression forces on the column. We'll assume that those are acting concentrically. And from whatever the glazing system is, we've got some point loads coming in from wind as well. So we've got 30 kilonewtons acting at 3 different locations along the height of the column. And what we want to do, first of all, I guess I haven't really talked about this very much yet, but we want to identify what NBC load combinations are going to be applicable here. We've got wind, snow, and dead load. We're starting to mix more than just a couple loads together, so it's not obvious what's going to govern. And for each of the load combinations, we're going to calculate U1x that we would use to check the interaction. Okay? Does anyone have any questions about what we're trying to do in the example before we get into the calculations? Okay. I've gone ahead and already drawn the shear force and bending moment diagrams. This is not a lecture on drawing shear force and bending moment diagrams. What's important here is what the moment is. It's 120 kilonewton meters. And the shape of the moment diagram comes from a series of point loads acting along the length of the beam. Okay. So basically what we need to do is figure out what the factored forces are on the beam and use those. I don't know why that keeps doing that all the time. Bring up a PDF, gets rid of the screen. But the first thing we need to do is look at what CEX would be. Basically, we need to figure out what U1 is. What CF is depends on the load combination we're using. We could use a couple different load combinations, and that's going to change CF. That means for each load combination, there's going to be a different axial load and a different moment, and the moment's going to be amplified by a different factor depending on the presence of the axial load. That makes sense, because if we come all the way back here, if CF changes, then CF delta changes. That means U1 is going to depend on the present axial force as well. Okay, so what we want to do is calculate U1x. To do that, we need an omega 1x, and we need to calculate CE. We've got a series of point loads giving us the shape of the moment diagram that looks something like what's shown on the right here. What omega 1 value do we use if we have a series of point loads acting along the length of the beam column? For anyone with the slide in front of them, or anyone who paid attention. I shouldn't say paid attention. Was able to memorize everything I said since the start of the lecture this morning. 1, that's right. So for members subjected to distributed loads or a series of point loads between supports, omega 1 is 1. Okay, so omega 1x, based on the shape of the moment diagram, because we have a series of point loads, that's 1, and that comes from 13.8 point whatever clause 6. So that was easy. Or I shouldn't say it was easy, but it's simple compared to some of the other steps. To calculate U1x, we need CEX, right? That's pi squared EIX over LX squared. This column, because of the presence of the Gertz, is laterally braced at the locations of the point loads, but it's not braced against compressive buckling about the strong axis. Okay, so this column could buckle this way, and so Lx for us here is equal to L, which is the 8,000 millimeters. So Lx is 8,000 millimeters. From the handbook for this section, if you were to look it up, why does that keep going away? This is very annoying. Okay, Ix is equal to 178 times 10 to the 6 millimeters to the 4th. And so CEX is pi squared times E, which is 200 times 10 to the 3 MPa, times 178 times 10 to the 6 millimeters to the 4th for Ix. All that gets divided by Lx, which is 8,000 millimeters squared. And what we get is an elastic buckling load. It's not the strength of the column, but it's just the load that would cause elastic buckling if the steel were strong enough, 5,490 kilonewtons. Okay, does anyone have any questions about what we just did or why before we continue on? Okay, so we need to figure out, right, when we're calculating U1, we've got CEX, check, we've got omega 1, check. Now we just need to figure out what CF is going to be. Now one might think, well, the biggest CF is going to give us the biggest U1, but the biggest U1 might be on a smaller moment, whereas a smaller CF value might give us a smaller U1, but a smaller U1 on a bigger moment. And when we're checking the strength of beam columns, it's not immediately obvious what's going to be important. Everything is important, and so a large CF might be governing over a smaller moment, but a smaller axial force might make the moment actually bigger based on the load combinations. This will be a bit more apparent if we look at the different load combinations we need to look at. Well, we've got dead snow and wind load acting on the column, and it might seem weird, how do we combine these together? Well, it's a little bit more obvious in the context of beam columns. We calculate CF based on the loads present on the column, and we use the moment that works based on the load combination. So this is the one for dead and snow that's going to maximize the moment because we've got some wind load as well. But we might also look at the wind load being larger than the snow. And so we could have 1.25 dead with half snow. That's going to make the compressive force smaller, but it's going to make the bending moment on the beam bigger. And which one governs is going to be a bit of a wash. Okay, so we're going to look at both of these first we're going to look at 1.25 dead plus 1.5 snow plus 0.4 wind. In this case, we have 1.25 times the dead compression load, which was 600 kilonewtons, plus 1.5 times the snow load, which was 300 kilonewtons, which gives us, that's CF equals, that's going to give us an axial force, I believe, of 1,200 kilonewtons, at the risk of losing my screen here again. Yep. And the corresponding MFX comes from the 0.4 wind term. That's 0.4 times the 120 kilonewton meters that we had from the moment diagram, and that gives us a moment of 48 kilonewton meters. Okay, so the 1.25 dead plus 1.5 S gives us our axial force. The 0.4 W gives us the corresponding bending moment acting on the beam column. Are there any questions about why we look at the load combinations in this way for this particular load case or combination before we continue? Okay. So we need to look at, for this load case, what's U1x? U1x is equal to mega 1x over 1 minus CF over CEX. Now we have all those terms. It's 1 divided by 1 minus 1,200 divided by CEX, which was 5490. And we end up with a U1x value for this particular case of 1.28. Okay? So the axial load on the column is about 20% or so of the elastic buckling load. So we have 1 minus 0.2 or so. Dividing by that gives us about 1.28. And what this does is it increases the moment present on the section from wind by about 28% when we include the U1x term in the interaction equations. Are there any questions about the calculation of U1x or how it applies before we continue? The last couple lectures are hard, I know. So that's only for this combination, right? So if we're looking at the interaction equations, we've got a big CF, which results in a big U1x value, but the moment is relatively small compared to the 120 kilonewton specified wind load. We might also look at 1.25 dead plus 1.4 wind plus 0.5 snow, in which case CF is 1.25 times 600 kilonewtons plus 0.5 times 300 kilonewtons. In this case, we get a factored axial load of 900 kilonewtons, which is smaller. But the corresponding bending moment comes from the 1.4 W. MFX is 1.4 times 120 kilonewton meters, which is going to give us 168 kilonewton meters. Okay, so the axial load is smaller, but the bending moment is bigger. And when we throw that into the interaction equation, it's anyone's guess as to which load combination is going to be more important for this member as a beam column. The one question I'll ask, though, we have a smaller axial force. Is that going to make U1x bigger or smaller? Remember that U1x is accounting for the additional moment from the axial force. If the axial force is smaller, there's less additional moment. U1x should be smaller. Right? So U1x now is equal to omega 1x over 1 minus CF over CEX. Very similar calculation as before, but now CF's different. 1 divided by 1 minus 900 over 5490. That's going to give us a U1x value of 1.20. Okay, so the P delta effect, or the CF delta effect, is smaller a little bit. We get a slightly smaller U1x value, which reduces the overall extra moment, but 20% extra of 168 is a lot more than 28% extra of 48. Okay? So the next step for us would be to plug these into the interaction equations. We have no idea which of these two load cases is going to be more critical in terms of the combined effects of compression and bending. But when we do the interaction equations, we have different values of CF, different values of MF, and the UNX value is also going to change between the load combinations that we consider. All right? So in the all we were doing in the example here is looking at the problem, figuring out what the corresponding factored loads were. For one load case, we got a certain value of CF. For CEX and omega 1x, that gave us one UNX value to use for that load combination. For the other one, slightly different value of CF, slightly smaller value of UNX to use in the interaction equations for that UNX value. Are there any questions about the example before we move to wrap things up for the morning? Okay, so we'll look at the strength interaction next day, because we'll see that this column is actually not class 3. But now you should be able to describe what's going on behind the scenes for the interaction equations for compression and bending, describe and account for that compression force, the P delta effect, and the effect of that axial force on the maximum bending moment when we have a member with compression and bending. And though we haven't done an example, work through applying those strength interaction equations to check a member that has combined compression and bending if it's a class 3 section. Okay, does anyone have any questions about anything that we've talked about today? That can be covered in 30 seconds before we wrap up lecture for the morning. All right, enjoy the rest of your snowy day. We'll see everybody Friday morning.